Hi guys, today we're going to talk about the normal distribution, also known as the bell curve. First, I want to recap some things we talked about last time and correct a slight notational error I had. So, notation. Last time we were talking about standard deviation, and there's a standard notation. So if x is a random variable, it's standard to use the Greek letter mu to indicate expected value. So this is expected value. And sigma to be the standard deviation. I said sigma, but I wrote a delta when I was talking about it last time. People will think you don't know your Greek letters if you were to do that. Alright, so that's just standard notation that we should all just understand, basically. I don't really care if you use it or not. And if it were unclear what random variable we were talking about, we might put a subscript by it. If it's clear, if we're only talking about a single random variable, then we don't need to, and we can just talk about mu and sigma, and it's understood. The other thing I wanted to talk about is I wanted to go back to the binomial distribution. So let's go back to the binomial. Distribution. So what is this? We did this a little while ago. So x is the number of successes after n trials, right? Where we have the probability p equals probability of success of each trial. So we have a formula for this. So recall that the probability that you get precisely k successes, the probability that x equals k, and k has to be between 0 and n, right? You can't get more than n successes if you only do n trials. This was equal to n choose k times the probability of success to the power of the number of successes, which is k, times the probability of failure, which is 1 minus p, to the power of the number of failures, which is simply n minus k. Okay, so this is all stuff we've done before. Now, the one thing I didn't mention is, so we also have that mu, so the expected number of successes is simply the number of trials times the probability of success, and then the standard deviation of a binomial distribution is going to be equal to the square root of n times p times 1 minus p. Alright, square root of all that. Alright, so we could go through the computation to show both of these things based on the definitions we have. It's definitely possible, but it would be quite a it's quite a little computation. So I think we'll just skip it. Hopefully you guys trust me that the formula is correct. Now I wanted to show you what these binomial distributions actually look like, if you'll bear with me. Alright, so let's see. I actually don't want to show this for now. Alright, so here we have, let's reduce, let's say we're doing 10 tosses. Let's deal with a fair coin. Alright, so this is what the binomial distribution looks like. So I'm using the model of a coin as our success versus failure, and we'll say success is getting heads, right? So if we toss a fair coin 10 times, these are the probabilities, and it's using the formula we just that we've derived. It's just a computer doing it for us. These are the probabilities. So it kind of looks like, you're going to get definitely it's very unlikely that you'll get something far off on the edges, and most of the time you'll get something near the middle, which is 5, right? Which is our expected value, 5. And if we change our expected value to 0.4, so this would be an unfair coin of 40-60. So 40% heads, 60% tails. It shifts it over slightly. Right now it's centered around 4, and it kind of shifts things around. Alright, so that's fine. Let's go back to fair coin. And let's say we have 100 tosses. Alright, so there's a lot of tosses, right? Now the curvature is really starting to be apparent, right? It's still clearly a blocky thing. We have, it's a bar chart. But now you can really see that it is basically flat at the edges, and then as we near the expected value, it curves up, and we have most of the probability concentrated in this region. Alright, now as we do more and more tosses, so let's do 200, the curve becomes smoother and smoother. And if we zoom in a little bit, we can start to see that it's looking like the shape of a bell curve. Let's do 500. Again, zoom in a little bit. Right. So the reason we want to study the bell curve at all is basically because it arises in this way. So now I'm plotting the bell curve, which is what we're about to study, and we see that it makes a very good approximation to this binomial distribution with a large number of trials. And the reason that is notable is because many things in nature arise as the result of combining many random variables together. And it turns out many random sort of processes together. So, and it turns out when you do that, you'll almost always get a bell curve. And we won't go into the mathematics behind why that is, but it's actually a sort of a deep theorem in probability that if whatever random variable you have, discrete random variable, if you combine it together, if you repeat it over and over again in independent trials, the net result when you add the number of successes together will always be a bell curve. So let's go back to the notes. So for example, so we get a bell curve for things like if you were to take the weight of infants, for example, infant weight, that's going to be a random variable, and it's gonna look like a bell curve. If we look at heights of 10-year-old maple trees, right, all these sort of natural things that are the result of many infinitely, well, not infinitely, but incredibly complex processes that contribute to like how heavy a baby is, or how the height of a 10-year-old tree, right? Like the actual biological processes involved are incredibly complicated, and there's many random processes going on. And because there's so many things that are combining together, we end up with a bell curve. another thing would be like something like the weather. If you were to talk about the rainfall in Boston on April 10th, right? You pick a random year and look at the rainfall in Boston on April 10th. That's also going to look like a bell curve. This is why, hopefully, this feels natural to you, but this is why we want to study bell curves, and it's going to be a little different than the discrete random variables we've been talking about so far. But first, let's talk about the shape. So, shape. Well, it looks like an inverted bell, right? Let's plot it. It's very low out on the edges, and then it comes up and comes back down. Alright, so I didn't draw it very well, but one key thing is that it's symmetrical. Let's say symmetric. About the expected value. So in this case, I drew it with the expected value as 0, but the point is that it's symmetric on either side of the peak. So the other thing is that the peak is also the expected value. So the peak is the expected value. So the really key thing about this is that it's actually not just any generic curve that kind of looks like this. So I drew it slightly sloppy, but it's actually a very specific curve, and it's completely determined by what the expected value is, so by mu, and by the standard deviation, by sigma. So if you know what the standard deviation and what the expected value are of a normal distribution, you know the entire curve. And well, I guess I might as well give you the formula. You guys are not actually responsible for the formula. So it turns out that the formula is, in this case, y equals 1 over the square root of 2 pi sigma squared times e to the power of -1/2 times x minus mu, all divided by sigma, and then squared again. Alright, so pi is that number from geometry that roughly equals 3.14159. And then e is maybe a constant it's not quite as famous as pi, but it's kind of similarly important, and is roughly equal to 2.71828. Alright, again, you don't really need to know this. I just wanted to give you the formula. So we have the formula, we have the curve. Or I guess one thing we will for now. We will be focusing on what's called the standard normal curve, which sounds a little redundant, but in this case, all curves that are of this shape, that follow this formula for some given mu for some given sigma, are they're a normal curve. And now a standard normal curve, or normal distribution, well, that's just if we set is when it's a specific normal distribution where the expected value is 0, so the peak is at 0, and the standard deviation is 1. So for now, we'll just be looking at that one. Well, this is the one we're going to look at in more detail. But first, let's just look at what these things look like in a little better drawing. Alright, so this is a picture of the standard normal curve. And changing our expected value is simply shifting it to the right or the left, right? So I can put that back around 0. And then changing our standard deviation is, changing how spread out it is. So if I increase the standard deviation, it'll get more spread out. And if I increase the standard deviation, it gets more pointy. Now you might notice something funny happening here, which is that if I make the standard deviation really small, the value actually goes above 1. And this would be something that would be impossible with our discrete probability histograms before, right? Because you could have no probability greater than 1 before. But this actually does happen, and nothing is breaking, and I want to talk about why that's possible right now. So, and basically what's going on is that we don't read off the height of the graph to get probability. So sort of the question is, how do we get probability from this curve? So to get probability, we look at area. So that's actually really important. Which means that we don't ask the question, so if x actually we'll use z. If z follows, let's say, a standard normal distribution, so it's a random variable that follows a standard normal distribution, we don't ask what is the probability that z equals 3, for example. That's actually not a question that we will really ask. Instead, what you would ask is, what is the probability that z is between 2.9, so 2.9 is less than z, and z is less than 3.1. So instead, we ask about ranges. And that's really the key difference between a discrete random variable and this thing, which follows a smooth curve, is that what we ask of our the questions we ask are the probability of ranges. And that's how that's the area that we look at. So let's see. Suppose that's a standard normal curve. So the probability that, for example, -1 is less than z is less than 1. So the probability that z is between -1 and 1 this equals the area under the curve between -1 and 1. So, and my drawing would be the geometrical area right here. And that's similar to what we had before. I don't know if you remember, but before, when we had our histograms of discrete random variables, we noted that the area under the rectangles actually corresponded to the probability. And that's the sort of the property. The reason that we mentioned that is because that's the property that carries over now to the normal distribution as well. It's the area under the curve that gives us the probability of a range. And what that means is that, so fact total area under the curve equals 1, right? Because you're guaranteed to fall somewhere. So the total area under the curve equals 1. And that's why the curve itself can be bigger than 1. As long as the total area under the curve isn't bigger than 1, then the actual value of the curve doesn't really matter. So if you look back here, right, when it gets really tall, the value is bigger than 1, but if we looked at the area underneath it, the area would still be 1, so we'd still be corresponding to a valid probability distribution. Okay, so how do we actually compute any of this? And it turns out there actually isn't a good way. There's no formula. There's no formula for this area. There's no formula. Oh, wait, sorry, I forgot to switch back. So there's no formula for computing this area. Now that might be frustrating, but in some ways it's actually good news for you guys, because it means there's no tricky computations for you to do involving the normal curve, because there's no formula for you guys to compute. But instead, what we use is a table, or in this class we'll be using a table. Now, in general, what people would use is they use a computer to compute something very accurately. That they can't use a formula, but computers can compute approximations very well. But for us, we'll be using a table, and it's a table of values for the probability that z is less than k. Okay. So this would correspond to the area right, if this is k here, then the probability that that z is less than k would correspond to the region to the left over there. I uploaded a table to the assignment, so you guys can have access to it too. It's just from the textbook. It's just over here. So this is a table of areas. So for example, and this is an approximation, and really we'll only be doing this to get a close value. So the first 4 digits are really all we need. So for example, so this is saying that the probability, let's just pick a number. So for 0, right, this is saying that the probability that z is less than 0 is 50%. The probability that z is less than 1 is roughly 15.87%. Right? So then the natural question is, well, how do we answer, for example, what's the probability that z is between 0 and 1, for example? Now, I just want to make a quick note here. It doesn't matter if you use inequalities, strict inequalities or not. Completely doesn't matter. It's the same area, regardless. So, yeah, just in case you were wondering, it just doesn't matter. So how do we compute this guy using this information in the table? Well, so if we know So the probability that z is less than 0 corresponds to this region, right, that I'm shading in black here. And the blue region, let's say this is equal to 1, corresponds to z being less than 1. If we want it to be between 0 and 1, we simply subtract the black shaded part, and we're just left with the stuff in between 0 and 1. So the probability that z is between 0 and 1 just equals the probability that z is less than 1 minus the probability that z is less than 0. So I take the right endpoint minus the left endpoint. And using the table, what we have is that this equals approximately, so 0.8413 minus 0.5 equals 0.3413. So it's roughly a third of the time standard normal curve. If your random variable is described by a standard normal distribution, roughly a third of the time it lands between 0 and 1. Alright, that's really all the theory for now. It is conceptually a very new thing because it's a continuous curve instead of a discrete distribution, but computationally it's probably the simplest thing we've done so far in the class. As in, we're just really taking differences between these values to get our answers. Now, one note: the probability that z is less than k is never 0. Is never exactly 0. Or 1. The curve actually goes out and out forever in both directions, and it's always above the axis. But it becomes so close to 0 and 1 very quickly. So, right, to 4 decimal places, you're already at 0 at -4, or you're already at 1 by 4. That's to 4 decimal places. But no matter how far out you go, there's always some non-zero probability. But that's just so we have the right mental idea of this. And then practically speaking, it goes to 0 pretty quickly. Right. So let's do the worksheet questions now. There's only 2. So sketch 3 different normal distributions on the same axis with the same expected value but a different standard deviation. Okay, hopefully if you've watched the video up to now, you have an idea of how to do that. Right. Recall what the animation looks like. Right, so you want to have the same expected value, so that's like its position right to left. And then we want is 3 different standard deviations. Right, so this is higher standard deviation, this is lower standard deviation. And the important thing is just that as it gets higher, it also has to get skinnier, right? So that area is maintained. So higher and skinnier, or shorter and fatter, basically. I'll let you guys do the exact sketching, though. Let's just talk about the second question. What is the area between x equals 1 and x equals 2 under the standard normal curve? Well, we have to refer to our table. So that is going to be so the table refers to an area function instead of probability of some random variable, so I'll just use that notation here. So this is just going to be area of our right endpoint minus area of our left endpoint. Right. So in the previous notation, right, this would be the probability that z is less than 2 minus the probability that z is less than 1. Right. There's a little more cumbersome notation, but you can use the more compact notation if you want as well. And we just simply look up what those values are. So 2 is 0.9772 minus, at 1 we have 0.8413. Alright, I'll leave it to you guys to do the actual arithmetic, and well, that's all for now. I'll see you guys in the next video or in office hours. Alright.